Hello friends, welcome to Civilization Civil 200 channel's new video. Today we are discussing about Geotechnical and Foundation Engineering Part 1. This subject is very important for all the civil engineering competitive exams and also for state and union PSCs. So friends, let's start our portions. Today in this theory portions we are dealing with Introduction to Geotechnical and Foundation Engineering, theories related to the subjects, and application of soil mechanics, origin of soil and soil properties, description of assemblage and individual particles. Introduction to soil mechanics. The material which is mantle in geology is called soil in soil engineering. Mantle is also called regolite. Soil mechanics is a study of engineering behavior of soil when it is used either as a construction material or as a foundation material. This is a relatively young discipline of civil engineering, systematized in its modern form by Carl von Tersaghi in 1925, who is rightly regarded as the father of modern soil mechanics. Application of the principles of soil mechanics to the design and construction of foundations for various structures is known as foundation engineering. Geotechnical engineering may be considered to include both soil mechanics and foundation engineering. In fact, according to Tersaghi, it is difficult to draw a distinct line of demarcation between soil mechanics and foundation engineering. The latter starts where the former ends. According to him, soil mechanics is the application of the laws of mechanics and hydraulics to engineering problems dealing with sediments and other unconsolidated accumulation of soil particles produced by the mechanical and chemical disintegration of rocks regardless of whether or not they contain an admixture of organic constituents. There are so many theories related to the soil mechanics. First one is wedge theory. Coulomb, a French engineer, published his wedge theory of earth pressure in 1776, which is the first major contribution to the scientific study of soil behavior. He says about concept of shearing resistance of the soil as composed of two components, cohesion and internal friction. Next one is Poslet, Kuhlmann and Rayban were the other men who extended the work of Coulomb. Darcy and Stokes' laws for the flow of water through soil and settlement of solid particles in liquid medium respectively. Rankine theory of earth pressure in 1857, he did not consider cohesion. Bosinic in 1885 theory of stress distribution in an elastic medium under a point load on the surface. Moore in 1871 graphical representation of the state of stress at a point called Moore's circle of stress. This has an extensive application in the strength theories applicable to soil. Next is the consistency limit. Attenberg, a Swedish soil scientist, gave in 1911 the concept of consistency limit for a soil. This made possible the understanding of the physical properties of the soil. Swedish method of slices for slope stability analysis was developed by Fellenius in 1926. He was the chairman of the Swedish Geotechnical Commission. Prandtl gave his theory of plastic equilibrium in 1920, which became the basis for the development of various theories of bearing capacity. Tersaghi gave his theory of consolidation in 1923, which became an important development in soil mechanics. He also published in 1925 the first treatise on soil mechanics. Thus, he is regarded as the father of modern soil mechanics. Field of application of soil mechanics. Foundation, retaining structures, stability of slopes, underground structures, pavement, earth dam. The load from any structure have to be ultimately transmitted to a soil through the foundation for the stability of the structure. Thus, the foundation is an important part of a structure. The type and details of which foundation can be decided upon only with the knowledge and application of the principles of soil mechanics. Next one is retaining structures. When sufficient space is not available for a mass of soil to spread and form a safe slope, a structure is required to retain the soil. An earth retaining structure is also required to keep the soil at different level on its either side. If Soil surface is not horizontal. There is component of weight of the soil which tends to move it downwards and thus causes instability of slope. Soil engineering gives the theories of earth pressure on retaining structures and methods for checking the stability of slopes. Underground structure. Design and construction of underground structures such as tunnel shaft and conduits require evaluation of forces exerted by the soil on the structures. Pavement design. The behavior of subgrade under various conditions of loading and environmental changes is studied in soil engineering. Earth dam are huge structures in which soil is used as construction material. It is used for creating water resources. If it fails, it may cause wide disaster. So, engineering study and knowledge is required. Next portion is origin of soil. By weathering of rock, by mechanical disintegration, by chemical decomposition, it obtained from geologic cycle. That is, rock obtained from geologic cycle. Geologic cycle consists of erosion, transportation, deposition and upheaval of soil. The processes we said in the geologic cycle is described in this figure. That is erosion, transportation, deposition and upheaval, and again this cyclic process continues and this original soil is repeating in the nature. After the original soil, we are going to study about the type of soil. There are different type of soil according to the place where it is originated and how they are transported. First one is residual soil. If the soil stays at the place of its formation just above the parent rock, it is called residual soil or sedentary soil. Next one is transported soil. If the soil has been deposited at a place away from the place of its origin, that is called transported soil. Again, the transported soil can be divided into gravity transported soil, alluvial soil, aeolian soil, glacial soil, lacustrine soil, and marine soil. First one, the gravity transported soil. Soils transported by gravity to short distances are called gravity transported soil. Example is talus. And next is alluvial soils. Soils transported by rivers and streams are called alluvial soils. They are known as sedentary clays. Aeolian soil. Soils transported by wind are called aeolian soil. Example is loess. Glacial soil. Soil transported by glaciers are called glacial soil. Example is glacial till. Lacustrine soils. Soil deposited in lake bed. Lacustrine sills and lacustrine clays are examples. Marine soils. Soil deposited in seabeds. Marine sills and marine clays are examples. In this figure, the type of soil is explained. Transported soil, again divided into gravity, glacier, water, wind, according to the medium which is transported. Get transported. It is again divided into gravity, glaciers, water, and wind. In the gravity type transportation of soil, it is called colluvial deposits. An example is talus. Colluvial deposits, an example is talus. And glacial type transportation, glacial deposits. Its deposits are called glacial deposit. Examples are echers, drumlins, glacial till. When water transport the soil, again it is divided into freshwater transportation and seawater transportation. Freshwater transportation again divided into streams and lake. The water may be in the streams or in the lakes. So, if the transportation is done by the streams, the deposits are called alluvial deposits, and if it is by the lakes, then it is called lacustrine deposits. Examples for alluvial deposits is shale sand sills, whereas examples of lacustrine deposits is warped marl. If the seawater transport the soil to a distant place, that is called marine deposits, and example is marine clay and marl. If the wind transport the soil to some distance, that is called aeolian deposit, and the example is loess and sand dunes. Next, we are going to study about the soil profile. The soil profile is a natural succession of zones or strata below the ground surface and represents the alterations in the original soil material which have been brought about by weathering process. It may extend to different depths at different places, and each stratum may have varying thickness. Generally, three distinct strata or a horizon occur in a natural soil profile. From top to bottom, these horizons are designated as A horizon, B horizon, and C horizon. A horizon is rich in humus and organic plant residue. This is usually evaluated and leached. That is, the ultrafine colloidal material and the soluble mineral salts are washed out of this horizon by percolating water. It is dark in color and its thickness may range from a few centimeters to half a meter. B horizon is sometimes referred to as the zone of accumulation. The material which has migrated from A horizon by leaching and evaluation get deposited in this zone. There is a distinct difference of color between this zone and the dark topsoil of the A horizon. The soil is very much chemically active of the surface and contains unstable fine-grained material. Thus, it is important in highway and airfield construction work and light structures such as single-story residential buildings in which the foundation are located near the ground surface. The thickness of B horizon may ranges from 0.50 to 0.75 meter. The materials in the sea horizon is in same physical and chemical state as it was first deposited by water, wind or ice in the geological cycle. The thickness of this horizon may ranges from a few centimeters to more than 30 meters. Upper region of this horizon is often oxidized to a considerable extent. It is from this horizon that the bulk of the material is often borrowed for the construction of large soil structures such as a dam. Each of these horizons may consist of sub-horizons with distinctive physical and chemical characteristics and may be designated as A1, A2, B1, B2, etc. The transition between horizons and sub-horizons may not be sharp but gradual. At a certain place, one or more horizons may be missing in the soil profile for special reasons. The morphology or form of a soil is expressed by a complete description of the texture, structure, color and other characteristics of the various horizons and by their thickness and depths in the soil profile. This figure shows the typical soil profile. First is organic matter. O represents the organic materials present in the soil. A is the zone of topsoil. B is subsoil region and C is weathered or decomposed rock area and R is a solid rock. This is how the earth different layers are arranged. Next we are going to study about the three-phase diagram. Diagrammatic representation of different phases separated in soil mass is called phase diagram. A partially saturated soil with the voids are partially filled with water and air contain three phases by solid, water and air. Hence it is called three-phase diagram. The figure shows the three-phase diagram and the actual soil mass diagram is in the first figure and the second figure how the arrangement of air, water and solid is in profile of soil. For better understanding and convenience, actual soil mass diagram is simplified in a simple diagram. This diagram is called a three-phase diagram. Here where the air comes and this is the water area and this is solid. In the three-phase diagram, if in the condition of fully saturation condition of the soil, it will become the three-phase diagram will become the two-phase diagram like this. Only solid and water is present in two-phase diagram. That is when the soil is in fully saturated condition. If the soil is in fully dry condition, then it also become a two-phase diagram, whereas air and solid comes. In the place of water, air comes because it is fully in dry state. So only solid and air is present in the dry state of soil, and also it is called a two-phase diagram. The diagram is called the two-phase diagram of dry soil. Typical three-phase diagram of the soil is showing here. Here, capital V. Capital V is the total volume or soil mass. and VV is the volume of voids. Volume of voids is equal to volume of air plus volume of water, and Vs is the volume of solids. Usually we represent volumes on the left side of the figure and weights on the right side. Next, WA is the weight of air. Usually it is taken as 0 or it is considered as negligible. This is weight of water, weight of solids, weight of voids is equal to weight of air. Capital W represents weight, total weight. Porosity of a soil mass is the ratio of the volume of voids to the total volume of the soil mass. It is denoted by the letter N and is commonly expressed as a percentage. N is equal to volume of voids by total volume into 100. Next is void ratio. Void ratio of soil mass is defined as the ratio of volume of voids to the volume of solids in the soil mass. That is E is equal to VV by Vs. Here E is the void ratio, VV is the volume of voids, and Vs is the volume of solids. Next we are going to study about the degree of saturation. Degree of saturation of a soil mass is defined as the ratio of the volume of water in the voids to the volume of voids. That is S is equal to, S is the degree of saturation, VW by VV. VW is the volume of water to the volume of voids into 100. It is commonly expressed as percentage. Next is percent air voids. Percent air voids of a soil mass is defined as the ratio of the volume of air voids to the total volume of the soil mass. That is, Na is the percent air voids is equal to Va, volume of air voids by total volume of the soil into 100. It is usually expressed as percentage. Thanks for watching. Please subscribe and like my channel.